Thank you, Chairman. Hello, everyone. My name is Chung from Postech Korea. Today, I will present a distributed cloud storage system called CYRUS. Okay. Do you think your data is really safe in the cloud? Actually, we found several articles about cloud failures and data leaks. Even though these failures and the data leaks are quite rare, people still concern the safety of their data in the cloud. Previous studies applied the storage techniques to client, which scattered the data to the multiple and different cloud storage services. However, we found that orchestrating many storage features and together at client has still many research challenges. So we propose CYRUS, client-defined, privacy-protected, reliable cloud storage. CYRUS provides the same user experience with existing cloud storage services. We implemented a client application as a prototype and figure out the practical issues. Okay, before explaining the details of CYRUS, I'd like to explain the design consideration. We do not trust any individual cloud providers, and the system should be scalable to the multiple clients with concurrent data access. We also need to select cloud where the data is stored. And finally, to avoid any dependency from any services, CYRUS does not require a central server or cloud-side code. Okay, to store file, CYRUS split a file into chunks for data deduplication. And then CYRUS encodes the chunks into shares with a non-systematic read-Solomon code. Let me explain the basic implementation decision first. To make the chunks from files, we use Rabin's fingerprinting, which is widely used as a content-based chunk approach. In fact, CYRUS supports version control, so the content-based chunking does not shift any chunk boundary when user modify a file. So in this point, content-based chunking has a benefit for CYRUS. To encode shares from a chunk, we use a read-Solomon code. Read-Solomon code generates any shares from a chunk, and to reconstruct original data, read-Solomon code need any T shares from N. It means end user allows N minus T cloud failures. However, read-Solomon code is not designed for security. For efficiency, read-Solomon code uses the same dispersal matrix, and even systematic read-Solomon code keeps the same data after encoding. So, to improve the security aspect, we generate a random dispersal matrix from a user's key string. We shuffle the sequence of the index, which does not impact on the optimal read-Solomon code implementation, but differentiate the code book per user. Okay, next, we need to design a cloud connector with existing cloud APIs. In fact, cloud APIs do not return any error from the concurrent user file upload, because they allows all write requests regardless of file existence. In this situation, we decide that implementing atomic operation using HTTP RESTful APIs is not the best solution. We also found that the file-based locking is inefficient. This is similar with the Wi-Fi congestion avoidance scheme. This does not provide or guarantee the fairness or scheduling, etc. So this needs the random backup and the several additional requests to check lock files. So we decided that CYRUS allows for clouds to create or overwrite file instead of controlling transaction. We design an addressing scheme that guarantee files with the same content are located at the same cloud with the same name. The share name is decided by the chunk content, and the location of shares are decided by the share name. If there are simultaneous requests to upload share, the shares are addressed according to each content, and there is no side effect from the cloud's file override or creating new file. To do so, we use a consistent hash that minimizes the share reallocation when we add or delete cloud. I will explain this aspect later. Okay. Unlike a share upload case, we can select the clouds optimally based on the performance from the client. We need only T shares from N of each chunk. Each client then maintains the history of throughput to cloud and minimize the download time using this formula. Detailed proofs are presented in the paper. In short, we use the bandwidth of CSPs as an input and decide this indicator D to download more shares from the faster CSP. Okay. This one is shows our metadata management scheme. So CYRUS also store metadata to cloud with read-Solomon encoding as well. We designed that a metadata file represents a file, represents an update of a file. A client synchronizes a metadata file before do any read or write operation. So, and then maintain the metadata as a local copy as well. Metadata maintains a file information such as a file ID, file size, file owner, etc. And then maintain the chunk map. So chunk map is an array of required chunks to reconstruct this file. And then this is written in the JSON. So JSON array keep the order of the sequence. So this is, and then the share map stores the location of each share in the cloud. Okay, so actually we also need conflict detection. So cloud detect the conflict locally. Because we cannot expect any support from server or cloud, so CYRUS built a version tree using metadata after synchronizing it from server. Okay. CYRUS can detect two different types of conflicts. So first one is creation conflict. So this creation conflict is the two different clients try to create a new file with the same file name. Second one is the update conflict. So in this case, two different clients can update a file from the same parent. So we can detect this conflict using our version tree locally. And then CYRUS consider the conflicted file as a new file with the different file name. So we just attach the timestamp to the conflict file. And then we can handle the conflict resolution easily. So user need to delete the conflicted file that they want to not to maintain. So this is similar with the Dropbox's file management scheme. Okay, so to add or migrate or delete cloud, we need to reallocate shares to the new or another clouds. So when adding a cloud, we actively reallocate shares. So consistent hash minimizes the number of shares to move. So in this example, we add CSP5 here. Okay. Then comparing with this, okay, this red dot represents a share, and then blue dot represents the cloud. So before adding the CSP5, the share is between the CSP4 and then CSP1 is located to the CSP1. But after adding CSP5, some shares between CSP4 and then CSP1 is located to CSP5. So we actively reallocate these shares only. Okay. When we migrate shares, we also actively reallocate shares as well. So, okay, we migrate the CSP3 to CSP5, then, okay, entire the shares in the CSP3 should be reallocated to CSP4. And then some shares between CSP4 and CSP1 should be allocated to CSP5. Okay. Unlike the cloud add or migration, we use lazy share recovery scheme for cloud delete. Because we should consider this case like user temporarily delete the cloud and then add the cloud later again. So before delete the cloud, we check if the cloud is deletable or not, considering the number of required shares. And then we just leave the every shares without recovery. So when user try to download or upload the same share, then if the client detect that okay, that share is not, the number of shares is not enough, then the client lazily create a new share and then upload it to a new location. Okay, this video shows our implementation. So our prototype uses the 4 commercial cloud storage services, and then I try to upload a photo to different cloud storages using CYRUS. So a file, this file is split into a chunk and then encoded into shares. Okay, and then each share is uploaded to the different clouds. The download, then we download the photo in different directory. Okay, photo is stored. Okay, and then download the photo again. Okay, so comparing with the upload, we just need 2 shares, only need 2 shares from 3 shares to download. Actually, this prototype is designed like a FTP client to show the every step of the upload and then download. And then now we are developing a second version, which is similar with Dropbox. So it supports folder synchronization with the CYRUS daemon. So we plan to release the second version at the middle of this year. Okay, so another practical issue is to detect the dependency among clouds. Actually, some CSPs or have deployed on the other CSP. So, for example, some clouds are deployed on the Amazon or something like that. Actually, we detected that 4 cloud services among 20 on this list have deployed on the Amazon. So we actually, in this case, there is a dependency of reliability. So if Amazon has failure, then the other services may affect on the failure. So to detect this, we used a simple proving using traceroute. So we try to make this proving tree from client and then detect the hop count and then the shared passes, and then we can find the dependencies among the clouds. So using this network proving, users can decide target clouds while considering the dependency. Okay. Actually, we simulated the failures, assuming CSP provide 99.9% availability, which is usually presented and described on the SLAs of most of CSPs in these days. We can see that the number of failures of CYRUS is more than 10 times smaller than a single CSP when a difference of n and t is 1. Actually, if the difference between n and t is larger than 2, equals or larger than 2, then we could not find failures until 10 million trials. Okay, so this is the in-lab environment. So we build our test bed using three slow CSPs and then 4 fast CSPs in our lab. And then we evaluate our optimal algorithm. So we compare the cloud selection algorithm with the heuristic and random selection. So heuristic means the round-robin selection. You can see that CYRUS shows the fastest download speed, I mean the completion time. And then throughput is also the, CYRUS shows the most fastest one. So, okay, you can see that the request faster than 4 megabps. Actually, CYRUS shows the 70%, more than 70% requests are faster than 4 megabps. And then we actually implement our CYRUS with the 4 commercial cloud services in real world. So we benchmark that. So we measure upload and download performance. We measured upload-download completion time to upload and download 40 megabyte file. CYRUS shows that shortest completion time except for the full striping. However, the full striping is a very extreme case that all shares of file should be available. So this is really extreme case with a poor availability. Comparing with DepSky, actually the DepSky was published in 2011 in EuroSys. We refer this study. So the DepSky uses the file-based RAG that I explained before. So we analyzed the performance, upload-download performance for each CSP. So you can see that due to the overhead of the random backup and then additional requests, DepSky should spend more time and shows the longer latency. But CYRUS is faster for every CSP. And then CYRUS, DepSky also accepts the fastest responses only. So you can see that the DepSky doesn't use the CSP3 because in this situation, the CSP3 was so slow. Okay, but due to this, their protocol, the DepSky cannot use the multiple storages in balance, but the CYRUS use the hash-based addressing for upload and then optimal selection for download. So CYRUS uses the storages in balance. This one is our deployment trial. So we recruit 20 academic users from US and Korea. And then we collect the logs from the CYRUS client program. So we noticed that the US is users in the clouds from US is very fast because of their shorter distance than Korea. In US case, the CYRUS, the cloud spend the entire link capacity at the client. So in this case, the bottleneck of the service is the client-side link capacity. But in Korea, due to the longer distance between client and then cloud, each cloud service provider cannot spend the entire link capacity of the client. So we can boost up the download and upload speed by requesting upload and download to different clouds simultaneously. Okay, the conclusion. So in this paper, we developed the CYRUS. We realized a client-defined cloud architecture by orchestrating significant storage features at client. We implemented a prototype and deployed it to users. our evaluation in real-world environment and deployment trials showed that CYRUS improves reliability and performance by coordinating CSP set client. Okay, thank you for listening.
Hi, Bill Belowski from MSR. So I'm trying to understand the fault behavior of your system. If I understood your write protocol correctly, you compute the data blocks and store them with content addressing, and then you write metadata, presumably to multiple clouds, right? So what happens if the client crashes when it's written, but the metadata to some but not all of the clouds? How do you deal with a partially updated write like that?
Oh, you mean the metadata crash at the client, right?
Yeah, so the client writes, say the metadata is replicated to 2 or 3 clouds. The client writes 1 or 2 of them and then crashes before writing the last one. Do you have a case where the data that you read then depends on which of the metadata servers you read from, or is there some way of coping with that?
Yeah, actually each client should synchronize the metadata with the server. So all the clients should upload their metadata after they update some files. So in this case, the client upload the metadata to the multiple cloud servers with the read-Solomon encoding. In this situation, the client can suffer, only partial requests are accepted. In this case, the client is very difficult to distinguish that between, okay, this is correctly, not uploaded because of failure, or this client is still uploading this metadata.
In both cases, so how do you determine that?
So actually we periodically retry the upload of the metadata, and then we just need to wait for them. And then actually they are the sufficient number of metadata to decode as uploaded, then we just accept it. And then then we just let them use it. But if not, then we cannot use the file.
And you can't use the file. Okay.
Yeah.
Thank you.
Thank you.
Okay, here. Alisson Bessano, University of Lisbon. What are your timing assumptions? Because DepSky works the way it works because you cannot trust that if a cloud doesn't answer, the cloud is out. Okay, maybe this cloud is only slower, or the network to that cloud in particular is lower. That's the first question. And the second question is, what kind of the consistency guarantee you provide?
Can you summarize the first question again? I'm sorry.
If do you write on quorums, or you write on like you have to write on two machines because you want to tolerate one failure, or in 2 clouds? You write on 2 clouds, or you write more?
Okay. Let me explain the second question first.
Okay.
The second question was
I can take that offline, but another comment is, the DepSky you compared with your code is the code available on the internet, or you re-implemented it?
Actually, based on the DepSky's implementation, we review the code, and then we extract the locking operations, and then we re-implement their code.
Because the values you showed are like 10 times lower than the values we take from Portugal.
Yeah.
I don't know why, but we can discuss offline.
Okay.
Have fun with the lunch and the good food, and thanks to the speaker again, I guess.